Welcome to RCast, the official podcast of the RChain Cooperative. RChain is a complete concurrent blockchain platform designed for maximum efficiency at minimal computational and environmental costs by utilizing proof of stake. I'm Derek Barris, the director of content for RChain. We cover a range of topics on this podcast, from the foundations of blockchain in general to the specifics of RChain, including our foundational language, Golang, as well as issues in calculus, governance, security, and the forthcoming businesses and dApp development on our platform. Please check out rchain.coop to learn more about our platform, as well as information on becoming a co-op member.
First of all, thank you, Derek, for hosting. It means a lot. I really appreciate your presence and engagement on this. And thank you to Isaac and Christian. It's always good to have a conversation with you guys, especially about these fun math topics. So I wanted to talk a little bit about the proof theory side of Ladle and sort of give people a perspective on what that means and why it's important, and the work that we've been doing most recently on that side of the puzzle. A lot of logicians and type theorists and mathematicians make a distinction between model theory and proof theory when they're talking about logics. The model theory lives on the side of semantics. So it's the place where you interpret your formulae. More recently, it's also the place where you interpret your proofs. So you build up mathematical models of the things that are your formulae. So for example, you can look at Boolean logic as a logical entity, and then you can ask for models, and those models are Boolean algebras. And you can look at modal logics, and you can ask for models, and those models are sets of worlds. You could even think of them as relationships across a range of Boolean algebras, where the relationships represent some kind of reachability notion you can get from here to there. And those are sort of the worlds that are mentioned in modal logic. And that interpretation, for example, was given by Kripke. Those are some examples of what we might think of as logic and model. And when we talk about model checking, which is an automated process, or at least that's sort of one of the aims, is to create an automated process. You're looking at the validity of the formula in terms of whether or not it has any models. If you come up empty, if the only models for a particular formula are the empty gadget in your model framework, like the empty set or the empty list or whatever your empty gadget is, then your formula is uninhabited and not valid. That's one way that you can go and check things. So for example, when you look at the Hennessy-Milner logics, which were proposed by Matthew Hennessy and Robin Milner for the pi calculus, that's done in terms of a model theory. The models of those formulae are exactly the sets of formulae that verify them. The sets of processes, sorry. The models of the formula are the sets of processes that verify the formulae.
Yeah.
So hopefully that's making some sense. Let me just check in with Christian and Isaac and just see if that piece of the puzzle makes sense.
Yeah, that makes sense.
Specifically regarding the Hennessy-Milner stuff, so you're saying that basically the interpretation, well, maybe that's not the right phrasing, but the way we think about a formula in terms of a model is in terms of the collection of processes that have the property that's basically expressed by the particular formula that we're dealing with, right?
Yep, that's it exactly. And by the way, that particular way of building a model is called realizability. So
yeah, right.
When your models are the computations that manifest the property, that's realizability.
Yeah.
There's another sort of fancy property that relates logic to computation and to category theory and type theory. And that's the Curry-Howard property. In Curry-Howard, and again, this was first observed, and then the more people looked at the property, the deeper it got. And so now it's kind of a property to demand or ask because it has such good benefits. And that is that your programs correspond to your proofs, and your types correspond to your formulae. So for example, you can get this by fiat. So for example, you can say that, we're going to build a type theory for process calculus, and those types are just the formulae that we provide for some logic for the process calculus. You get it by fiat, right? You get it for free because you're saying, we're sort of taking on Curry-Howard as a requirement of the system. It was originally discovered, right? So people were working independently on intuitionistic logic and the simply typed lambda calculus. And Curry and Howard noticed this correspondence between the types of simply typed lambda calculus and the formulae of intuitionistic logic, and wrote down a translation between the two. And then later people discovered that there was a correspondence between the proofs in simply typed lambda calculus, in intuitionistic logic, and the programs in simply typed lambda calculus. In particular, the thing that's of interest is that the cut rule corresponds to the formation of application, which is a formation of what's a reduction expression, or a red X. And there's a theorem called the Cut Elimination Theorem that says that every proof can be transformed into a proof that doesn't use the cut rule. And that's very much like normalizing a lambda term by running beta reduction wherever your applications have a lambda expression in the operation position and something else in the argument position. So those two things, beta reduction, cut elimination, correspond to each other. So you get this really tight correspondence in the simply typed lambda case between the notion of computation and the logic that you use to reason about it. The two branches were done independently, and then they noticed that there was this deep correspondence. And then later, through the work of Abramsky and others, it came to be realized that this is kind of a desiderata, a collection of desiderata to have when you're designing a logic, is that it should have this property. And in fact, the whole ladle program grows out of recognizing that when you demand both realizability and Curry-Howard, that kind of nails down your notion of logic considerably. There's not a lot of wiggle room in terms of what a logic can be. And this is just an extension of what Abramsky was noticing in his pioneering work on domain theory and logical form, where he would start with a domain theoretic construction, turn a handle, and derive a logic. So Ladle is doing something similar. We've talked about the model theory side, but I also have been sneaking in this idea of a proof, and there's the whole proof theoretic side. But before we jump there, I just want to make sure that everything I said up to that point sort of makes sense.
Yeah.
I wanted to say thanks for the history lesson on all of the Curry-Howard correspondence stuff. I hadn't heard all of that linked together, and then also bringing it all back to Ladle. That was really cool.
Oh, yeah, no, my pleasure. I mean, I really hope that this information doesn't get lost, right? Because it is really fascinating that, intuitionistic logic and the simply typed lambda calculus were developed independently. And that the correspondence was only noticed post facto.
Yeah.
In some sense, it's a bass-ackwards way of approaching things. That's fairly typical of how mathematics is developed. It's like people are following intuitions which are closely related, but not knowing that they're converging towards each other until they talk to each other. Initially, when I formulated the basic examples driving the Ladle research, it was all on the model theory side. And I was well aware that ultimately we were going to have to come up with a proof theory. That what we were looking for was, to algorithmically generate a proof theory such that it had a cut elimination theorem. So you can see the cut elimination theorem is essentially driving the shape of the proof theory. What we're going to see is that the formation of every term constructor is going to correspond to the introduction of a logical constructor. And then you also have the constructors for the collections. And then whenever you have term constructors that form reduction expressions, so again, we're talking about an arbitrary rewrite system with the property that it's interactive. So without loss of generality, we can say that interactivity means that you have a term constructor that's binary in the left-hand side of your rewrite rule. And whatever happens on the right-hand side is not constrained, but the left-hand side must be a binary term constructor. So it has to take two terms. Now you can have more than two, but we don't have to consider ternary, quaternary, etc. We don't have to consider the n-ary term constructors because they can all be boiled down to binary.
Okay, I think I that was something I didn't understand when I looked at this at first, what you meant by interactive, but you just mean that the terms interact with one another, right? And
that's
why
correct.
We want multiple. Okay, cool.
Yeah. So the one thing you can't have is a term that doesn't have any internal structure, just evolving on its own.
Yeah. Okay. Right.
Right. So just like some constant magically turning into some other constant.
Yeah. Right.
That we're eliminating that. Those kinds of rules are typically called heating rules, where a lot of term rewrite systems sort of lend themselves to chemical analogies, and it's not surprising because if you look at chemical equations, they are exactly term rewrite.
Yeah. Why is that called heating rule?
When you look at those kinds of rules in the chemical context, such a transition would happen when you're applying heat.
Yeah.
Right.
Yeah.
So it's the same. It's the same sort of intuitions.
Yeah.
I've always thought of heating rules as having terms being knocked out for context, and then you're evaluating the term and putting the result back into the context.
Yeah, you could think of it that way, assuming that
Okay.
you've got some kind of context rewrite situation.
Right. Yeah.
And in fact, that's a nice foreshadowing of what we're going to do. What we're going to do is closely related to blockchain and to RChain specifically. We're going to modify these rewrite rules and add, a resource. So you have to, again, following the chemical analysis, we're going to add a catalyst. And without the catalyst, what was originally a regex becomes inert. And it's only in the presence of the catalyst that you get the rewrite rule. So that's what we're going to do. But before we get there, in terms of the proof theory side of things, whenever we're forming a regex, we're using the binary operator that would create a term that's on the left-hand side of the rule. We now get two kinds of proof rules. One kind of proof rule forms it without the catalyst. And so essentially it's forming a data structure that has all the information you would need in order to perform a computation except the catalyst. In the presentation we're talking about today, the catalyst has no interior structure, no internal information, right? It's like we're just adding this constant on the side that enables the rewrite rule. The other formation the other proof rule we'll make is one where you form the regex and you add the catalyst. So that gives us proof rules that mark the computational potential and computational actual. Sorry, my dog is putting her butt on the steering wheel. That's essentially how we're forming the logic. There's this one piece of the puzzle I'm leaving out intentionally for this discussion, and we'll circle back to it, but that's the basic shape. So let me just check in and see, does this make sense to you guys? We're going to build logical formulae that correspond to the collections. So an example in the case where your collections are sets is, one formula would be true. Another formula might be or, which would correspond to union, or true corresponds to, all the terms in your language. Union corresponds to a disjunction. Those logical operators come from the collection piece. And then there's a logical formula introductions of logical formulae made by using the term constructors from your rewrite system to build up formulae. So as an example, if your rewrite system is the row calculus, the par constructor is a term constructor, and you can use that to form logical formulae as well as just terms, right? So you could do true, par, true. That would place a demand that your process is at least composite. And so it's got at least 2 threads. So that's an example. And then there's further elaboration so that when you make terms that are on the left-hand side of a red X, you get 2 rules. One for making that term but without the catalyst, and one for making the term with the catalyst. So does that make sense?
Yeah. What was your original motivation for the catalyst?
So the original motivation for the catalyst is to prevent reduction in unwanted contexts.
Yeah.
And we noticed at the time that we were doing it that this was closely related to introducing, resource constraints on notions of computation, providing models of what happens in blockchain.
Yeah.
So it had kind of 2 benefits, and so it seemed like a reasonable thing to take a look at. And here we're continuing to reap the benefits of this idea. Those are the proof rules. So now it's kind of easy to see whenever you form proofs that have a red X with a resource, then you can eliminate that from your proof by simply replacing it with the right-hand side of the rewrite rule. If you do the types right, the types will remain the same. You get a cut elimination theorem by design. You get it for free.
Yeah.
This is a lovely property. And what it does is it forces us, it follows all of the demands that we're making, right? So we're insisting Curry-Howard, we're insisting that we have realizability. So all of those things are kind of shoving us into this box. There's not a lot of degrees of freedom for the design of these logics, which is exactly what we want, right? We want this to be algorithmic. We don't want to have any creative steps. They all have to be dictated essentially by the shape of the input that we're being provided, which is the notion of collection, the notion of term, and the rewrite rules. The next piece of the puzzle has to do with how this relates to, well, actually there's several pieces. One is, how does this relate to linear logic? And how does this relate to various notions of computation? And where is the negation in all of this? So with respect to linear logic, what we can see is that when you form the left-hand side of a rewrite rule, when you form a red X and you don't supply the resource, then what you've got is a tensor. I said we're forming a data structure, but we don't actually have the right to call it a data structure until we can extract the data from that gadget. All right, so whatever the term constructor is, if we can't pull the data out of that term constructor and do something with it, then it's just stuck there. It doesn't do anything until we apply some resource to it, and then it can evolve. If we want to give it some utility, then we have to be able to extract it. So dual to this tensor, we just, again, algorithmically add a term that allows us to access the components. And that's going to correspond to the linear logic par. That will cause us to add another cut rule in which we cut a tensor with a par. And then there are essentially 2 kinds of ways to do that. You can cut them end on end. So again, we've demanded that the system is interactive. There's some term constructor, call it K, that is binary. We have 2 of them effectively, right? So we've got a K and the par, which can extract the things from the K. So the par is like the shadow of the K, or it's dual to it. We can now either plug these terms end on end. So we can, let's say the 2 terms are T1, T2, U1, and U2. So the T1 and T2 are formed by the term constructor K, and the U1 and U2 are formed by the par. You can form a K of T1, T2 and a k of u1, u2. So that's end on end. Or you can form a k of t1 and u1 and a k of t2 and u2. I don't know if you can picture that in your mind, but one is essentially wiring things up in series and the other is wiring them up in parallel.
Yeah.
That breaks the thing down into essentially two flavors of extraction. You can get two logical operators like that. And so that gives you a sense of how this kind of corresponds to linear logic, with the exception of what's going on with negation. All of that stuff is very straightforward, easily verifiable. I'm not worried about any of that stuff, even though this is, I'm giving you a preview into work because we haven't written it up, we haven't published it or had it peer reviewed. But that part is fairly easy to see that it just works. Now the next bit is much more speculative and potentially controversial, but is quite fun to think about. As background, what we're using to construct the proof theory, we're following the guidelines or the guideposts set out by Abramsky. If you look at his paper, Computational Interpretations of Linear Logic, he essentially retroactively or reverse engineers a notion of a term which he calls a proof expression that exactly lines up with the linear logic formulae as types. He does this for classical linear logic. We're basically using that as a template to build our system with the extra added guidance that we use the R as the thing to suspend computation. I should also mention that we're using R in a kind of punny way. So it's not just resource, R for resource, it's also R for reflection, in the sense that without the R, when you form a red X, you've essentially suspended computation. So this is just like call CC kinds of discipline and scheme or other functional languages. I'll make the connection even to delimited continuations in just a minute. And this is all related to how we think about negation. And then when you have the par and the tensor together, that gives you the ability to disassemble suspended computations and potentially modify them and then reassemble the suspended computations and then add a resource and reflect that back. So forming a red X without an R is what's called reification, because you're now taking everything that you would need to have in order to make a computation in the original system, but you're denying it the resource to actually run, and so it's suspended. But so it's all packaged up as a data structure. And again, I strongly recommend look at 3Lisp and Rosette and the other reflective systems. This is exactly the recipe for the sort of procedural or functional reflection part of the puzzle. And then pulling things apart and modifying them, doing some compute on them, on those data structures, and then putting them back into place and then adding an R, that's called reflection. So you have both reification and reflection. And we're using these capacities to their fullest extent in formulating the proof theory. This is one of the ways that we depart from Abramsky's recipe. But it's already present in Abramsky's recipe in the sense that he has a two-part sequence. So when you form these assertions that a particular term in your term language gives you or satisfies a particular type, that kind of expression is called a sequent. And his sequence on the term side, the terms have two pieces. One is kind of some advertised site of interaction, and the other is a body where some computation is in a potentially suspended mode. And that body is nested. So it's not just that you have computations suspended, but you have this whole tree of suspended computations. And each of those represent resumption points. And that's in particular how he's using that to model the with and plus side of linear logic and the of course and why not side of linear logic. logic.
What do you mean by
So that
resumption?
basically continuation.
Oh, yeah.
Yes.
Yeah.
Where you resume the computation.
Yeah.
The trick is to recognize that R provides a context for either reflecting or reifying computation. And if you give it enough structure, in particular, you allow it to form trees or other kinds of data structures, then you get back all of the machinery that Abramsky was getting with his bipartite structure for the terms. That's the intuition there, and then that's closely connected to the notion of negation in the following way. So you think of a negation as A arrow false or A arrow empty, and then when you doubly negate, you should get back to A. Now, you don't necessarily get back to A, which is why we have a thing called intuitionistic logic, but you can insist on closing it up. So you're only looking for the terms where negating twice gets you back to where you started. And that gives you what's called an involutive negation, in the sense that, not A is A, as opposed to, not A is not A, which is the intuitionistic case. And now you can start to see that just by looking at the types, we're saying that A arrow something, whatever that is, that looks just like a continuation. And in particular, if you go A arrow something to something, right? So A arrow R to R. I should have picked a different letter than R. The reason I chose R is because if you look at the types of the maps that you use for the continuation monad, they look just like that, and R is the result type. So what we're saying is that the notion of negation is closely connected to adding sufficient structure to R to model a notion of not just resuming, but a whole stack of continuations or resumptions.
Okay, yeah. Could you go over that kind of more slowly?
Sure. It's easier if we had a whiteboard.
Yeah. A lot of this.
Yeah. What we're saying is, and again, I strongly urge looking at the literature here. There's a close connection between, again, the scheme call with current continuation and the law of excluded middle. And essentially, you can view it as either I have an A, or if you think about it in terms of the R-chain tuple space or R space, either I have an A or I've suspended my computation until I have an A. And the suspended my computation until I have an A, that's A arrow, whatever the type of the resultant computation is. I think you see where that's going. And then so now we're explicitly talking about suspending computation. Well, how do we suspend computation? Well, we suspend computation by withholding the resource. Now we can do better than just simply withholding the resource. We can create a resource context which is marked as suspended, either because it doesn't have something or is in some other state. And so that's what I'm talking about, giving the resource additional structure. And we know that ultimately, if we're going to model things like the blockchain, the resource itself has to have a kind of counting structure, right? We have to be able to have multiplicities of R. When you use it, right, you have to spend it down. So equations like R par R, or R applied to R, or whatever your term constructor is, equals R, can't hold if you're going to use R to model resources like flow or the Ethereum gas. Thank you. Yes.
Yeah.
So if you're going to use R to model gas or flow, then R has to have at least the structure of multiplicity. So you have to be able to add them and subtract them. So that's expanding the structure of R. And now comes, the coup de grace, or the really cool stroke, which is that if you don't want to import through R a foreign notion of computation, but you know that R has to have additional structure, where would you get this additional structure?
I mean, just making it more than a constant, making it an interactive term in the language.
Where would we get that term structure, right? If we don't want to import a foreign notion of computation.
Oh, I mean, from the term calculus itself.
Exactly. You can do a reflective trick.
Yeah.
There are two that are available and applicable. I've already talked about one extensively, and that's where you make R be a context.
Mm-hmm.
Right? So a term context. And then the context term pair is a location, and that gives rise to the whole space calculus.
Yeah.
So you can use the space calculus to model this extensively, and that's one solution. Here's another solution. I've mentioned the whole red-black sets. For people who haven't been following RChain forever, it's a cool trick. So you imagine a set theory made with red curly braces and a red element of predicate, and another set theory with black curly braces and a black element of predicate. And red element of cannot see into black curly braces, and the black element of cannot see into red curly braces. This framework, this setup, gives you the ability to model things like Frankel-Matowski set theory without leaving the safety and comfort of a set theory that arises from empty, right? So you don't have to take on the risk of this whole universe of atoms. You just have to have two distinct copies of set theory that are recursively interdefined. The atoms for the red set theory are the black sets, and the atoms for the black set theory are the red sets.
These elements represent either active or inactive computation.
So you can do the same thing. For example, you can take the row calculus and you can make a red row calculus and a black row calculus. And then the black terms are resources for the red calculus. And the red terms are resources for the black calculus. And so now you have as much structure as you want in your R, but you've kind of isolated them. They're not interacting, right? You don't have to worry about any interference on your R resource from the computation that it's enabling, and vice versa.
How do you know which element to pick that has the right structure?
So there you just use whatever coding tricks you've used before, and we know them quite well. I mean, you just use the entire structure, and you just code up what you need for whatever structure of R you want to supply. So if you want multiplicity, in the case of the row calculus, you only need the par operator and some things that don't interact, right? They just get eaten away. An example would be if you just want multiplicities, then you use the church-style encoding of the naturals into row, and that's your R. Right, so now you have exactly the multiplicity structure, and it's isolated from interacting. And of course, once you've done that, then you can compile it down into just an ordinary row without this red-black bifurcation by doing a namespace discipline.
And you're saying that would afford you a catalyst that you can treat like flow or some kind of computational resource?
That's exactly right. And so now we've tied the whole thing together, right? We've sort of said, here's how you derive your proof theory, and we're deriving the proof theory. Here's how the notion of resource connects to the notion of negation, and here's how you can impose different. And remember, so there's some context that I keep around in my head that maybe not other people do, which is the whole monadic account of delimited continuations. So if you peer into that work, what you discover is that they're essentially keeping a data structure for resuming. In their case, the data structure is a stack. In Abramsky's case, because he has concurrency, the data structure for resumption is a tree. And you can use whatever data structure you want that supports the kind of resumption strategy. And that resumption strategy is intimately related to notions of fairness and notions of liveness and yada, 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 which is, again, closely connected to the points that I was making about error correcting codes. But now we've got this framework in which all of those connections are elucidated, precisely how the negation is related to your resumption strategy and how that resumption strategy corresponds to structure that you demand from your R. That's all laid out in a kind of algorithmic fashion. So if you want particular properties of your negation, that turns into properties that you demand of the R structure, and then you go demand those of your term calculus. So you get this nice kind of recursive encoding. And then that lays out, by and large, the shape for the proof theoretic side of ladle in such a way that we get this correspondence between the reduction in the rewrite system and the cut elimination in the proofs. So I don't know. I think that's it's a pretty construction.
At the point where you're talking about how to implement the resources, you said you could have either gone the route of the space calculus or with these red-black sets. How do you connect those two strategies, and why would you prefer one over the other?
Yes. So with red-black, you don't have a clear notion of location. So with the space calculus, the reason it has that name is because we have this clear notion of location that derives from UAs. So if you want to have a notion of location, that if that's somehow important to your computation. So for example, suppose that we wanted to reason about failure, located failure. Now we're in the situation where we're reasoning about distributed systems, and we want to be able to talk about regions of failure. Then the space calculus is a better tool for the job because there's a crisp notion of location.
Yeah, it seems like a really comprehensive solution for a lot of the issues that we talk about.
Right. In the other case, if you don't yet have a notion of location, then you can just use the red-black construction for the calculus.
I was going to say, I don't know if it's just me, but it doesn't seem like a coincidence that we can get this notion of kind of an algorithmically generated proof theory from this ladle algorithm, and this naturally supports a notion of resource, which you can then even program further and make it, even support a notion of like some kind of computational effort or, flow or something like that for like blockchain purposes. So I just wanted to maybe hear your explanation of like how all of these things fit together so nicely. It doesn't seem like a coincidence.
You know what? To my mind, it's very, very much like the history of Curry Howard. I've been trying to hold all the pieces together in my mind, but I did not have a clear understanding of how they all fit together until the last few weeks. I'm genuinely surprised that there's this notion of resource that's related to resumption. That negation, resumption, and resource are all recursively intertwined. Mm-hmm. In retrospect, it's like, duh. Right? Like basically what you're saying whether you're talking about Ethereum or any other smart contracting platform that uses a resource to control computation, you're saying the resource has the ability to suspend computation. That's your assertion. Right. But it didn't dawn on me. Well, yes, but that's effectively continuations, right? Right. And so it has to be related to negation. Connecting the dots has been this slow, laborious process. I wish I were faster at it. But I don't think it's a coincidence. But I don't know that anyone has put all the pieces together this way. So we seem to be pushed into pioneering efforts.
This is very nice.
I think I'm going to have to listen to this again to fully understand everything you were talking about. But yeah, this has been a really cool discussion. And I guess I even left something out of my characterization there, which is that it also supports realizability and Curry Howard correspondence.
Yes, so that's exactly right.
Even nicer.
Well, but the thing is it's actually, but if you take those as your starting points, those are your demands for your logic, then everything else kind of falls out. We're backed into this, and that's basically what the ladle journey has been all about. Is like, right. Well, this is my line in the sand, right? I can't violate those conditions. Mm-hmm. And everything else is just the implications of having those as your design criteria. Cool. Well, I appreciate it. So Christian, what we really need now is we need nominality.
Yep.
If we can have the nominality, then I think we've got a really, really lovely account of logic. I mean, there are some desiderata. So, for example, I would love to be able to extend the notion of collection to past set-like gadgets, but it doesn't seem to be a way to do that and have a distributive law. So there something has to give, and I don't quite know what that is yet.